Okay, I think it's time to drink out of a fire hydrant. Here on the left is what I call the hidden structures diagram. It has a majority of the structures and mappings that we will be looking at in this book and in this course. What I thought we would do, however, is simplify this diagram for now, just to get us into the mode of understanding what it is we're doing. And so that's what I've done here. I've simplified. I'm going to focus on just those three structures for now, just these three. Okay, and I hand drew it, so it's not as pretty as a computer rendered diagram there, but hopefully it's readable. Okay, I'm assuming that the viewer has watched the first, I think, 6 class periods of the course. And so some of this will be built on the assumption that you have already seen some of the words, some of the concepts are somewhat understood already. If not, you may be able to follow what we're going to do. In fact, that's the purpose of what I'm doing now, is to try to give a simple analogy of what's going on during those 6 class periods. Okay, well, the first thing I need to define is a Bessey structure. Now, we are assuming here, unfortunately, that you know what a positional relation is. And in my upcoming analogy, I think you'll get a sense of what that is. So I think that will actually become clear in just a few minutes. A positional relation. And what that does is it's an equivalence relation on the relative positions of these objects here. So we have 2M elements, and sometimes I refer to them as objects because you can think of them, and we will think of them, and I will demonstrate these ideas with physical objects. So we have an even number of objects on which we have them in some initial state, some initial ordering. And so pi here is just a permutation on the set of objects X. So we have some initial arrangement right here. So we have a positional relation defined, and we also have a categorical relation defined on the set of objects. Now, all that means is we have different features, characteristics, qualities, or properties of these objects that allow us to put them into distinct groups, especially groups of interest or of importance to us. So we'll see examples of that in just a minute. So just imagine they're in different categories, maybe blue ones and yellow ones and red ones, if you want to think of balls or something. And we say that this, now it's quite a mouthful here, this quadruplet is a Bessey structure if and only if this happens right here. Okay, so we have a set of objects, we have some initial ordering, we have an equivalence relation that gives us a structure relative to positions of these objects, and also we have an equivalence relation that puts these objects into distinct categories whose union is the whole set of objects. Okay, so let me show you or try to explain to you what this means. The brackets, of course, is just equivalence class containing these particular objects. So let's try to make that a little clear. So what this inequality, what this subset relationship is describing is it's requiring us to do the following. It simply means that if the objects are related by position, then we require that they be related by category. So to put it simply, if objects are in positions relative to each other that are important to us or special to us, then we want those objects to also be of the same kind in terms of the category into which they fall by way of our categorical relation here. Okay? Um, so also recall from the reading, if objects are related by position, we say that they are P equivalent. That is short for position equivalent. And I made up that word, so you won't find that anywhere, I don't believe, especially not in this context. Um, if the objects are related by category, they are called C equivalent or category equivalent. Okay, let's get to an analogy here. Okay, suppose we have an even number of empty boxes with the numbers 1, 2, 3, up to 2m clearly labeled on the boxes. These boxes are bolted to the floor, cemented. They don't move. They will stay where they are for all eternity. So these boxes stay put. They are empty. Now we're going to put objects into these boxes. And of course, the boxes are just representing the positions in which we will place the objects. So suppose we have 2m objects. These objects come from one or more categories of interest to us. The 2m boxes don't move. The 2m objects may move. Each box must contain exactly one object. Okay, so that's setting the stage to understand Bessey structures. So the first kind, which is just right over here, that 2 capital C, that stands for a 2 cycle. And here the C is capitalized. So in the lectures, you know that that is telling us something different from the meaning that a 2 cycle, small c, would mean in the study of permutations. Okay, so we have adopted the word cycle because it fits. It describes what's going on. I will always use a capital C. In fact, it will always be paired with a number here, 4 and then hyphen cycle, 6 hyphen cycle. And these will always be an even number of cycles. Okay, so right here, this 2 cycle with a capital C, so far right now, we haven't defined it. We don't know what that is. So we say that the 2m objects form a 2 cycle if for all boxes Q and S satisfying this, namely, they need to be congruent modulo M. The objects contained in these boxes come from the same category. Okay, so a 2 cycle is simply essentially a pair of equivalence relations in which if they are related by position, they need to be related by category, as we've mentioned right here. Okay, so let me just read that one more time. We say that 2m objects form a 2 cycle if for all boxes, Q and S, satisfying Q is congruent to S mod M, the objects contained in these boxes come from the same category of interest. And those categories were set up at the beginning or need to be set up at the beginning. So when that happens, we're looking at what's called a 2 cycle. That's the structure of the sequences over here of objects. It's given by what we have written down. Okay, Now, what's a mirrored structure? Well, we say that the 2M objects are mirrored if for all boxes Q and S, and I'm going to be OCD here and underline that for consistency, if for all boxes Q and S, satisfying Q plus S is equal to 2M plus 1, or it could also be the case that Q is equal to S. If that relation holds for these boxes Q and S, then we require that the objects contained in these boxes come from the same category. Now you may want to think about, what does this do? What condition does that put on the relative order or positions of the boxes? And we'll see what that is in a minute. Finally, for an AMP, which is down here at the bottom, we say that the 2M objects form an AMP. Now, AMP actually just stands for adjacent mirrored pairs. That's where the term came from. We say that the 2M objects form an AMP if for all boxes Q and S satisfying this, the objects contained in these boxes come from the same category. And this one as well is it ends up being a fairly simple relation to see and practice, but ends up being fairly difficult to write down precisely. So that's called an AMP. Okay, so let me show you examples of each of those. Okay, so I have here 8 cards. Okay, so how you need to begin is you need to decide, what will the categories of interest be for the cards? Now, an obvious one here would be the relation that the cards be of the same value. So the relation could be 2 cards are related in this set of 8 cards if it is the case that the cards have the same value. So what that would mean then is we would have ace, the aces would be related by way of this categorical relation. The 2s would be related, the 3s and the 4s. Okay, so we do have a pairing that we've set up or had in mind, or maybe is imposed on us given a certain application. Okay, so if we go with that as our categories, so essentially the categories are aces together, 2s together, 3s together, 4s together. And of course that partitions the set of objects into disjoint sets whose union is the whole thing, hence it's an equivalence relation. Okay, well, let's go back to the 2-cycle for a second, because that's essentially what I've set it up. I've set it up in a 2-cycle relationship. Okay, so recall we say that the 2M objects, 8 objects form a 2-cycle if for all boxes Q and S satisfying this, the objects contained in these boxes come from the same category. Okay, now we have already talked about in class what Q congruent to S mod M is. So what does it mean to be Q is equivalent to S mod M? Well, it just means that the remainder when you divide Q by M, and the remainder when you divide S by M, those remainders are the same. That is a way, that's not technically the definition, but it's a proposition that follows immediately from the definition of congruence. So these two numbers have the same remainder upon division by m. Now, of course, m in our case is 4 because we have 2m, in other words, 2 times 4 or 8 objects. Okay, so what does that really mean? Well, let's focus on, let's say, the first positions right here. Okay, so what are if we label these 1, 2, 3, 4, and then 5, 6, 7, 8. Okay, in fact, let's put them in a box arrangement here, sort of. Okay, so here is the original ordering of these objects. Starting, this is the first object over here, second, third, fourth, fifth, sixth, seventh, eighth. Okay, so let's focus on the aces for a second. Look at their positions. This is position 1, this is position 5. Is it true that 1 is congruent to 5 mod 4? It is, because 5 divided by 4 gives you a remainder of 1. Same thing here. Divide 1 by 4, and you get a remainder of 1. So these are congruent modulo 4. So what that would mean is the boxes 1 and 5 are related by our positional relation. Okay? Now, is it the case that in those boxes, the two objects in those boxes are related by way of our categorical relation? Well, we stated that our categorical relation put the cards into disjoint sets of cards of the same value. So the answer is yes. These are from the same category. Over here, this is position 2, 3, 4, 5, 6. Position 2 and 6. Are those numbers 2 and 6 congruent modulo 4? Yes, because 2 divided by 4 has a remainder of 2. 6 divided by 4 has a remainder of 2 as well. So these are related by way of our positional relation, and they happen to also be related by way of our categorical relation. Okay, I think you get the idea. I don't know if we need to do all of these, but this is position 1, 2, 3, 4, 5, 6, 7. Is it true that positions 3 and 7 are congruent, that those numbers are congruent modulo 4? Yes, they are. 3 divided by 4 gives you a remainder of 3. 7 divided by 4 gives you a remainder of 3 as well. So what we're looking at here is, right as I laid out initially, is a 2-cycle. It is, in fact, a 2-cycle by our definition. We looked at the mirrored structures next. Okay, so to remind you of what those are, we say that the 2M objects are mirrored if for all boxes. Now remember, this is box 1. Imagine a box there and a box here, 3, 4, up to box 8. Okay, if for all boxes Q and S, it is and satisfying this equation here, this set of conditions, that Q plus S is equal to 2M plus 1, or we're allowing Q to be equal to S. We need it to be the case that the objects contained in these boxes come from the same category. Now, if you remember, the category that we set up for the 2-cycle structures was that the objects of value, or the cards of value, the cards of interest needed to have the same value. So an ace is related to an ace, a 2 is related to a 2, and so forth. Okay, so if you recall, Those were, in fact, maybe we'll use our language relative to a 2-cycle. The aces are p-equivalent. Relative to a 2-cycle structure, the 2s are p-equivalent. Relative to a 2-cycle structure, the 3s are p-equivalent, and so forth. So in terms of the positions, that's what we just finished a moment ago. Now, what we're looking at here is something quite different. We need it to be the case that Q plus S, when added together, gives you the total number of objects plus 1, or we allow Q and S to be the same. Okay, so let's first focus on that requirement just to get an idea as to what is going on there. So, as you may recall, this is position 1. This is position 2, 3, 4, 5, 6, 7, 8. So if you want to imagine empty boxes with those numbers written on the outside, in which we have placed, for now, these cards. 1 card in each box, okay? So we're focused on the boxes right now. So what boxes have numbers that would add up to 8 plus 1? So what boxes have numbers written on them that would add up to 2m plus 1, which would be 8 plus 1. In other words, 9. So as you think about the positions 1 through 8, which positions add up to 9? Well, the first position and the last position, because this would be 1 plus 8. Well, 1 plus 8 is 9. The second position and the 7th position, well, 2 and 7 also add up to 9. So these are related by way of our mirrored structure as far as positions. Over here, position 3 and 6, well, 3 and 6 add to 9. And then 4 and 5, positions 4 and 5, well, 4 and 5 add to 9 as well. So in a mirrored situation, we're really just looking at the reflection of each other relative to positions, okay? In fact, that's why it was called mirrored. Now, we cannot say that this is a mirrored structure relative to the categorical relation we used just a moment ago for 2 cycles, because the categorical relation there was that 2 cards are related if they have the same value. Well, look, is it true that the first and last one have the same value? No. Same thing here. Those are not of the same value. Those, nor are those. So we cannot say this is a mirrored structure relative to cards of the same value. But we can say that this is a mirrored structure relative to the equivalence relation that cards add up. In fact, I need to be careful, not equivalence relation. Relative to the relation that cards have values that add up to 5. Now, if you remember in the reading, I pointed out that this particular relation that 2 numbers add to a fixed number is not reflexive nor transitive, but it is symmetric. And the symmetric property will never be relaxed in the study of cyclic and mirrored structures. But there are times when we're looking at categorical relations that just by the nature of the relationship, reflexivity or transitivity may not even make sense. But the symmetry condition is absolutely required. Okay, so going back to what we were talking about here, what I'm trying to do is I'm trying to salvage something out of this current arrangement. Now we know that we can look at this as a two-cycle. Great. Can we also look at it as a mirrored structure? Well, there is a fairly easy way of doing that, because if we look at the card in the first position and for the card in the eighth position, their values, the values of the cards themselves, add up to 5. If we come in, because that's what we do with a mirrored relationship, we just kind of come in equal distance from either end. Okay, what about these two? The two cards in this mirrored reflection of each other. Do the values of these cards add to 5? Well, yes, they do. What about these two? They are reflections of each other relative to position from the center. But equally important, the value of the cards sitting in these positions, these two positions, their values add up to 5 as well. And the same thing for the cards in the very middle. So what we can do is we can state that this is a mirrored structure relative to card values that add to 5. So we are requiring that position 1 and 8 have cards in them whose card values add to 5. We are requiring that the cards in position 2 and 7 have values that add to 5, and so forth. So this is actually an example of a mirrored structure if we just change the categorical relation we have in mind. Now, you can also see that if we were set on using our original categorical relation that two cards need to have the same value, then a rearrangement of the cards in this fashion would give us a mirrored structure relative to that categorical relation. Because now the mirrored pairs here, the pairs that are reflections across from each other relative to position, also are related to each other relative to card value being the same. So if you remember, the original categorical relation for the two-cycle was the requirement that the cards have the same value. And the ones in the position 1 and 8, yes, those cards have the same value. The cards in position 2 and 7, they have the same card value, and so forth. Same, and then the same. Okay, so this list here of cards, we can use it to create two fairly natural mirrored structures. Okay, so that is a mirrored structure. The last kind of structure we're going to look at is an AMP. Okay, so what is an AMP? We say that the 2M objects form an AMP if for all boxes, positions, Q and S, satisfying this. And the objects contained in these boxes come from the same category. So this requirement here is just restricting or telling us how positions of objects are related. And once again, we also need to have a relationship among the objects that's of interest to us, or one that we set forth and then need to consistently use. Okay, so if we wanted to continue to use the original categorical relation that two cards are equivalent if they have the same value, which is what we did for our two-cycle, then what we'll need to do here is rearrange these cards in the following way. And there's not just one way to do it, actually. And I should have pointed that out for the last couple of examples. But we'll go with perhaps the most obvious kind of pairing here. Okay, so if you notice what's happened, cards of the same value, and we're going to go with that as our categorical relation, are adjacent. They're neighbors. They're right next to each other. Okay, well, what is this requirement right here? What is this saying? So we say that the 2M objects form an AMP if for all boxes Q and S, satisfying this, that the boxes have objects that are of the same category. Well, what is really going on here? Let me grab a piece of paper. Q minus S is equal to 1. And try not to reach over the camera. Okay. Well, the definition, the description came after the intuition and the exploration. So what this is describing is what we have right here. We have what are called adjacent pairs of interest. Okay, so is it true? So what we're going to do is just show you that these two positions are related by way of this equivalence relation. Well, this is position 1 over here. So why don't we say Q is 1. This is position 2. S is 2. Okay? So first off, is it true that the difference, hopefully you can see this, it's kind of small, sorry about that. Is it true that this is equal to 1, the difference? Well, it is. 1 minus 2 is negative 1, and the absolute value of negative 1 is 1, so that's fine. So that's kind of the first requirement in this pair right here. We also need it to be the case that the minimum of Q and S, well, it's 1. And the question is that odd? It is. It's an odd number. Okay, why do we have this condition here, do you think? How is that requiring that we're taking objects in pairs from the top, from the beginning of the sequence? Well, it won't take much exploration for you to see that what we don't want to have happen is we don't want these two related by way of their positions, right? So there, in that case, Q would be equal to 2. This is position 2. This is position 3. Okay. Well, if we look at Q minus S, is that equal to 1? Well, it is. But we don't want those related. So that's why we have an additional restriction. It also needs to be the case that the minimum of Q and S be odd. Minimum is odd. Is that the case? Well, no, it's even. The minimum is 2. Okay, so that prohibits these two from being, quote, related. So what these conditions here, the first part of this condition simply requires cards to be related in pairs from the beginning of the sequence and then shifting over in a non-overlapping way. Okay, so that is just a way to require it. And then to get a proper equivalence relation, we allow Q to be equal to S. And there's no danger in doing that, just having every card related to itself. It poses no difficulties for us. Okay, so that's what an AMP is. And by the way, so we were just focused on the positions for now, but because I rearranged the cards, I did it in such a way that these special pairs now consist of cards that are related by category, the categorical relation that two cards are related if they have the same value. That is met as well. So we can say that this is an AMP relative to cards having the same value. So an AMP is describing the positions of important pairs. And then we need to also be clear on what are the important pairs. Well, important pairs here are cards that have the same value. Okay, great. So that is an example of an AMP. Now, I do want to point out that given a random group of 8 cards, and these are just randomly, I have these have been mixed quite a bit, so I have no idea what these are. If you put out 8 cards, okay, it was looking kind of boring because at first it looked like they're all black, so that would not be all that much fun to look at. Most of them are black. Okay, let's say somebody gives you 8 random cards, as we have on the table here, and you were to just set those out. You could probably just fan them in the sense of just show them like that, 1, 2, 3, 4, up to 8, because then you can quickly close them up without any kind of maybe suspicion or something. Because right now, if you have them out like this and you very carefully pick them up, they're going to think, okay, why are you worried about how you're stacking those? But if this is the random arrangement of random cards that they give you, what you can do is either in your mind's eye or on a piece of paper. Let's do the piece of paper one right now. So under the guise of simply just writing down the card values, that's what they think you're doing, and you can say, I'm just going to write down the cards you gave me. So we'll do S for spades, and then next to it, I'm going to write 10 of spades. And then on my paper, I'm going to write 9 of clubs, followed by a 6 of spades. And then the next one will be 10 of hearts, followed by a 10 of clubs. Finally, we have 3 of diamonds, next to a 6 of clubs. Okay, so these are just written down. You could fold the piece of paper, kind of put it out of the way, or have it face down or something. And then the cards are put back in the order in which I suppose you could even justify that, because picking them up in the same way that they were handed to you, because otherwise they will think you're doing something sneaky. So this truly would be, move that, this truly would be the cards that they randomly chose in the order that they handed them to you. Okay, so what you've done on the paper is you've set them up as an AMP. Well, you might wonder, well, what categorical relation do we have in mind? We've created one. Cards are of the same category if they're on the same line that we've written. So we say 4 of spades and 10 of spades are related, or in the same category. 9 of clubs and 6 of spades in the same category as each other, and so forth. So this is a partitioning, a set of 2 objects, 2, 2, 2. The union of those is all of them. So this gives rise to an equivalence relation. Okay. You may recall that anytime you partition a set, which simply means you divide it into non-empty disjoint sets whose union is the whole set, that automatically, immediately gives rise to an equivalence relation. And we say two things are equivalent if they're in the same subset. Okay, so what that means then is I have an AMP relative to these categories. I'm sitting here with an AMP relative to those categories. Well, if I were to mix these in some way, I did a left-right shuffle. This is called a Charlier shuffle, if you remember seeing it. It's quite a messy shuffle. And then maybe we'll throw in a Klondike shuffle for good measure. And then, maybe we'll even throw in one of these. And we'll even kind of mix those up how they're stacked there. And then what we're going to do is we're going to put out pairs. Okay? And then you show the pairs. And this will mean nothing to the spectator. They'll go, okay, so what? Go, oh, well, that's really interesting. I don't know really how that happened, but I wrote down these cards in pairs at the very beginning. Let's see, I have a 4 of spades and 10 of, oh, wow, look at that. 4 of spades and 10 of spades. I also have a 9 of clubs and a 6 of spades. Oh, wow, here it is. 10 of hearts, two tens of opposite color. A 3 of diamonds and a 6 of clubs. How in the heck did I do that? Okay, so that's where our diagram comes in. So we've talked about the basic structures. Now the question is, how do you go from one structure to another by way of some very common and believable mixing procedures? And they do mix the cards. They truly do mix the cards. They may not randomize the cards, but they mix the cards. But they mix them in such a way that structure that we want survives. So if in our mind's eye, we have a packet, we've imposed an AMP structure on it, and we treat it as an AMP, which means you respect that structure relative to the mappings, quote, the shuffles that you put it through, and follow where that structure goes. Now, these are homomorphisms and automorphisms that we'll be looking at. But if you can keep track of the mappings that you've applied, their effect, you can reveal incredible things that will absolutely blow away the spectator. Now, this is only 8 cards. Imagine 26 cards in which you paired them up perfectly. Their heads will explode, I promise you. Okay, so let's look at, we finally got back to our primary structures and mappings. So let's look at what is going on here. So what I want to do here is essentially just practice some of these. Now, proving that they are conversions between the different structures, well, that's has been and or will be shown in class. We're simply going to practice moving from one structure to another by way of these various mappings. Okay, now as I pointed out, we could actually just use a random set of an even number of cards and show you everything here. But to be able to follow things, to make things a bit more transparent and more readily understandable, let's go ahead and let's go ahead and use what we were doing before. And so you can choose different cards if you like. You could choose the 4 queens and the 4 kings if you wanted. There's so many different relations, categorical relations you can put on a packet of cards. And of course, there's a near infinite number of categorical relations that you can put on, sets out there of a large number of things. We're back to the very beginning, the 2-cycle structure that we had. Okay, so that puts us over here. Now, something I did with that one example of using random cards is I actually performed a Charlier shuffle. Okay, so a Charlier shuffle, many of you know this because we've talked about it in class. So this is where you push off a number of cards from the top, and then from the bottom, in fact, I have a video on the Charlier shuffle, so you may want to look at that if I go through the steps for that too quickly. So you top to bottom, bottom to top, top to bottom, bottom to top. Now, despite the fact that that looks pretty messy, and it looks like it would be impossible to know where things are, and in some ways that is true, because I can do this with my eyes closed, right? And then at that point, I truly don't know exactly the order of the cards. I can't tell you what card's on top, for example. But I do know that a Charlier shuffle is equivalent to an ordinary cutting of the cards. Now, cutting of the cards is where you just take a certain number, you don't rearrange anything, take a certain number, put those down, and then the rest on top. That's a cut. Believe it or not, the Charlier shuffle is equivalent to one of those. So, in particular, what that means then, to prove it, okay, that's pretty amazing. I got back to there. We should be one cut away from the exact order we had before. Well, we are. If I just move these to the bottom, that's where we started. Okay, so a Charlier shuffle, despite its just messiness and the perception that you really are just mixing those cards. And what's interesting is even when I tell people, if I don't tell everyone, but when I tell people that a Charlier shuffle is really just cutting the card once, they will not believe me. They will not. They say, that is mixing the cards. I'm absolutely convinced that is mixing the cards. And I try to show them through example, and some of them eventually believe me, but it's such a convincing shuffle that it's actually hard to change people's opinions. Okay, so the Charlier shuffle is indeed equivalent to a single cut. Now, what that means in terms of our structures and what we talked about in class is the Charlier shuffle as a mapping is an automorphism. It is an automorphism. Why is that? Well, as we mentioned, let me just do it again, this time so that we don't get the exact same order. What does it mean to be an automorphism? Now, I know we've already talked about this in class, so I apologize for the review. But so an automorphism is a bijection from a set. Well, first off, you have to have a set with structure on it. It can be algebraic, topological, some kind of structure. And an automorphism is where that structure is preserved. The key structure or the key requirement for the structure of that entity is preserved. Okay, well, what is truly the requirement of a 2-cycle? Let's go back and review that. Well, a set of objects is a 2-cycle if the following is the case. If p-equivalent cards are related by way of our categorical relation. Now, our categorical relation for today will be that the cards have the same value. Now, because of the cards we chose, it's also the case that they have opposite colors. So you could throw that in if you want. Same value, but opposite color. Here, it wouldn't make any difference. You don't have any other choice. There's only a red ace and a black ace and so forth. Okay, so we need it to be the case that p-equivalent cards are of the same value. Okay, so remember, this is in position 1, this one's position 5. Sorry, 1 and 5 are congruent to each other mod 4. And it's because 1 divided by 4, well, that's a remainder of 1. And 5 divided by 4 gives you a remainder of 1 as well. So if you remember, these are p-equivalent, and they're also of the same value. So there you go. These are p-equivalent. Look at their positions. Divide their positions by 4, and you'll get the same remainder. These are p-equivalent, and these are p-equivalent. Okay? And I probably should start using the C-equivalent word as well. It just saves saying a lot of words. So remember, two objects are C-equivalent if they are in the same category. So the categories that we've set forth here are sets that have cards of the same value, okay? So here, going back, we could say the threes here, they're both p-equivalent and c-equivalent. The fours are p-equivalent and c-equivalent. The aces as well, and the twos. Okay, now you might think the original two-cycle we had was nicer, because we had them in order, ace through 4 of clubs and ace through 4 of hearts. Well, maybe that's the case. It appeals to our aesthetic sense of order, and all is right with the world to have it that way. But as far as the definition of a two-cycle, what we are looking at right now on the table is just as legitimate of a two-cycle as the original one, because we just need p-equivalent cards to be c-equivalent. That's all that original subset relationship, wherever it is, that's all this is saying. The cards that are p-equivalent need to be c-equivalent, okay? That's all we're doing. Okay, so this is the two-cycle. And so what we've learned or seen or been reminded of is the Charlier shuffle. You can think of a shuffle as a permutation or a mapping, is an automorphism. It leaves two cycles alone. Now, you cannot apply the Charlier shuffle just willy-nilly to these others. Create a mirrored structure and convince yourself that you can't just randomly cut that and expect the cards to be mirrored anymore. Okay, so now, as an aside, I hope to not give you too much here. As an aside, there is a Charlier shuffle that preserves all of these, and it's one that I've come up with the name because it's not out there. People don't talk about it, but boy, is it valuable in the study of cyclic and mirrored structures. I call it the Charlier 1. The Charlier 1. So what the Charlier 1 does is, let me put this one back in that original order that we started with. Sorry, if you can see that. A Charlier 1 is where you just move one card at a time. Now, it's not as sloppy and maybe as convincing as a traditional Charlier shuffle, but boy, it still looks like you would have to be a genius to keep track of where things are. Okay, so this is where you push off the top, 1 from the bottom, 1 from the top, 1 from the bottom, 1 from the top, 1 from the bottom, 1 from the top, 1 from the bottom. Now, I don't know how many people would be able to immediately conclude that what we've done is we've just done a 50% cut. but that's what it is. So a 50% cut just means we've taken the top half, which this was the top half, and we moved it to the bottom. Okay, well, why would a Charlier-1 actually be an automorphism on these other categories of structures? Maybe I shouldn't use the word category, that we're using it in lots of different ways, and the collections of structures. So why would the Charlier-1 preserve a mirrored structure? Well, it doesn't take much to convince yourself that that is the case, because if you have a mirrored structure and you cut it in half, it's still mirrored. It's not exactly mirrored in the precise way it was before, but it satisfies all of the conditions for a mirrored structure. Okay, well, it ends up that mirrored structures have a classic automorphism, and this is not one that I've discovered. It comes from something called the stay-stack principle, the stay-stack principle. And maybe we'll talk about that in more detail and perhaps even prove it later in the semester. It's not too difficult to prove. There's a bit of bookkeeping. There's kind of a matrix involved to keeping track of where you are when you perform a left-right shuffle or a more general RC shuffle, I call it. So here what I have for the moment is I have, this is mirrored relative to cards having the same value. Okay, so mirrored relative to cards having the same value. Great. Well, it ends up that an LR shuffle preserves mirrored structures. And what is fantastically wonderful is it doesn't matter if you stack right on left or left on right. The mirrored structure is preserved. Okay, so this will still be mirrored. Now, it won't be the exact same arrangement, right? Hopefully people are starting to get a picture for that. The cards are being mixed, but within certain bounds that you understand, or at least we understand some of what we're doing. There's so much, I'm sure, that none of us understand when we mix things up. But I have given you the tools to understand this much, that this is mirrored, because what we need, I guess you can just call them mirrored pairs. They need to be sequivalent. Sequivalent here means that the cards have the same value. So these have the same value, those have the same value, these have the same value, and so forth. Okay? And once you have, well, maybe we can show it now down here, but you have to realize that once it's mirrored, you're one slick step away from pairing them, right? If it's mirrored and you go like this, you've paired them in value. Sorry, that went flying. You've paired them in value. Well, that's the Klondike shuffle. So if you start with a mirrored structure and then perform a Klondike shuffle, you will get an AMP. And the way that we've done it is we've gotten what's called a DMP, distinct mirrored pairs. Well, what's an AMP is where you perform the Klondike shuffle and you're stacking the cards as you go. What I've done here is the pairs are all over the place. So this is called distinct mirrored pairs. I'm sorry, we're kind of moving on. Remember the chart that I showed you. So here we go. DMP, distinct mirrored pairs are off over here. And you can do special things with those. But so anyway, I apologize if I'm throwing too much at you at once. But the fact is, once these are paired together, to get an AMP, it doesn't matter what order you stack these, which is wonderful. Okay, so many times you see card effects and people are very carefully picking up these pairs in just the right orders. We don't care. it's an AMP. Anything I could do with an AMP, I'll be able to do with this packet. Okay, so this is an AMP. Okay, so there you go. Remember, p-equivalent cards here mean that they're adjacent, starting from the top, and non-overlapping as pairs. Okay, so first pair from the top, of course, are the aces. They're the same value. Fours, the twos, and the threes. So that is a bona fide AMP that satisfies our categorical relation. Okay, now it ends up that AMPs have a tremendous number of automorphisms on them. You can do even size cuts. An even size cut just means maybe I cut 2 to the bottom. Well, think about it. That's not going to change the fact that it's an AMP. You can do even size coats, 1, 2. That doesn't change anything. Well, it does change things. I need to be careful. It does change things. Things are changing. But the fact that this is an AMP is not changing. We're staying within the whole world, the whole universe of AMP packets, given our equivalent cards. Also an even deal. So we could do 3, 4, 5, 6. Rest on top. Oh, well, I guess that's a deal. That's kind of a coat. And I guess what we could say here is that, in fact, I'm trying to remember exactly what I had in mind there, as far as because a coat is a deal in which you put the the rest on top. But it is true that you can deal these out into even piles and then stack them in whatever order you like. And it's the same thing with a coat. Okay, let's put these back here. So maybe we'll coat 2 of them, put the rest on top. It doesn't matter if I put those on top or move them, right? Because it comes back to a even size cut. And then you can even flip an even number of cards. Okay, it's not going to change the fact that these are related, right? So you can go like that, and then I can come over here and then maybe flip these 2 as well. This will still be an AMP. Now you have to realize that this is pretty transparent only because of the categorical relation we chose. If you think back to the random collection of 8 cards that we put out, and I paired them up perfectly at the end, if we were to do this, these pairs would have no connection at all in the minds of the spectator. They have no connection. The only connection they have is the fact that you put them into categories on your secret piece of paper. Okay, so even though this is like, oh, well, there's something obvious going on there, it doesn't have to be, right, in general. Okay, so anyway, that's an AMP, and a Klondike shuffle will get you from an AMP to, from a mirrored to an AMP. Now, let's say we want to go back. We want to go back to a mirrored structure. Well, we can do a mange shuffle. And what's nice here, once again, it doesn't matter which variety you use. You can do an over-under or an under-over, and both work just fine. Okay, so a mange, to remind you, this is where you push off the top card. And then let's do over-under first. So then the next one goes over, under, over, under, over, under, over. That converts an AMP to a mirrored structure, guaranteed. So here we have mirrored again, right? And once again, it wouldn't matter if we had done under over. So to quickly get back to go from a mirrored to an AMP, let's do a Klondike again. This time we'll just stack them on top of each other, which is normally, that's what this means here, Klondike. You're just stacking them as you go. And to show you, of course, you get an AMP, which is what we want. And now let's do an, whoops, you can't see my finger. An under, over. So now push off the top, under, over, under, over, under, over, under. Well, does that take us back to a mirrored structure? It does. It takes us back to a mirrored structure. Now, it won't be the exact arrangement of cards that we got with the over-under. And so people's perception that cards are being mixed is correct. The cards are being mixed. But once again, they're being mixed in a way that you have some or significant knowledge over how those cards are related to each other given their positions. Okay, so the structure is preserved if we're, careful, if we have structured preserving maps. Okay. Okay, so you can go from, and depending on if it's even or odd, an even or odd size packet, I don't have the result right here in front of me, but the Klondike and Mange are exact inverses of each other under the right condition. I'm trying to think if it's like the over under is the inverse when you have an odd number of cards, and the other one is the inverse if it's under over. All of that's actually listed in the book. I give you the exact inverses. Okay, great. So what we're going to look at now is we have an AM. Nope, we're back to a mirrored. Okay, well, since we're over here at a mirrored, let's go ahead and jump this way. Now there's an arrow that goes both ways. And C here is a 50% coating of the cards. Okay, so we have mirrored. So if we do 1, 2, 3, 4, that's half the cards, drop the rest on top, we will get a 2 cycle. And you're getting a feel for how the cards, they're not super mixed yet, but how, well, they will be as we continue doing this, but the cards will be changing places but maintaining structures depending on where you are in this diagram here. Okay, but this is a 2 cycle. P equivalent cards are C equivalent, right, as you go through them in pairs. Now we could have actually, and I've mentioned this in class, a 50% coat, technically this goes on top. Well, something called a super coat, it includes more than just what I'm going to show you now, but a super coat includes the case where you stack them in the opposite order, meaning you stack them in whatever order you like. So once you've counted out half the cards, you can stack them in either order, and guess what? It's still a 2 cycle. Okay. Oh, sorry. It's still well, here we've gone back to a mirrored. So it's still a mirrored. Okay, so let's get back to a 2 cycle. Now, to get to a 2 cycle, we have a couple of paths. We can do another 50% coat, or we can do a mange. A mange. Okay, so that, and it can be of either type. So we'll do over and then under, over, under, over, under, over. Okay, so that will take our mirrored structure to a 2 cycle. Okay, so here are the P equivalent cards are C equivalent. Okay, great. And then while we're over here, you can do a Charlier shuffle, do as many of those as you like. Each one of those is equivalent to an ordinary cutting of the cards. If we want to get back to a mirrored, a 50% coat always works. So in a just immediate sense, a 50% coat is an isomorphism between 2 cycles and mirrored structures, and given the constraints that we are looking at, like even size packets and so forth, right? So a 50% coat is an isomorphism between those structure types. But why don't we instead of going that route, let's follow a Klondike. And in some ways, it shouldn't be a surprise that the Klondike will take us here because it is essentially the inverse of this one. What can happen is you don't necessarily get the exact order back, but you get the reversal of the packet. Well, guess what? All of these structures are unperturbed by reversing the cards. If you flip the sequence, if you flip a 2-cycle, it's a 2-cycle. If you flip I flip meaning the top becomes the bottom becomes the top kind of thing. If you reverse the order of a mirrored structure, it's still mirrored. If you reverse the order of an AMP, it's still an AMP. And packet reversal for everything that we will do is of no consequence. It doesn't prevent us from accomplishing what we would like to. So, okay, so anyway, where did we get? We got back to a 2-cycle, right? Okay, so we've done that. So how do we go from a 2-cycle to an AMP? Now, on my larger structure, I actually don't list the ferrule shuffle, but it's actually there. It's there in 2 steps. So you can get to it by way of, let's see, I think you go from here to there and then from there to there. So if you look at what the ferrule shuffle is doing, it's kind of consists of 2 steps. You're cutting the cards in half and then you're interlacing them. So the ferrule shuffle is not listed as going down, but it's actually there. It's just the composition of 2 mappings. So, okay. So here I just view it as an honest goodness standalone mapping. So the whole set of actions is going to be viewed as just one process. Okay. So once again, 2-cycle. So a ferrule shuffle. How does a ferrule shuffle work? Well, that's where you have the card. You split the cards in half. So you split them in half. 1, 2, 3, 4. You split them in half. And then there is what's called a ferrule in and a ferrule out. Either one works. Hooray! We don't have to worry about in or out. So what's a ferrule in? Well, so if you remember, let's see, what did I do? This was the top. This was the bottom. Okay. So a ferrule in, that's the first one listed. Okay, what you do here is, for it to be an in, this top card, this one right here, needs to eventually go under the top card there. That's why you say it goes into that packet. Well, the way that you do it is you have to begin with this one going lower than that one. So you go like this, and all you're doing is you're just interlacing those perfectly. That's a perfect ferrule shuffle, is what it's called. And in fact, it's a perfect ferrule in shuffle. And it will always take a 2-cycle back to an AMP. Always, always. And if we had done a ferrule out, it would have worked equally well. Okay, so maybe we'll show you just one more thing because this video is getting quite long. We haven't gone from an AMP to a 2-cycle yet. And the way to do that is by way of an LR shuffle. And there are other ones, not very many. There's another one as well that we probably should show you, but it's on our larger map, a diagram. So the LR. So this is an AMP. An LR is where you go left, right, left, right, left, right, left, right. We can do random stacking of the cards. That will take us to a 2-cycle. Always, 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 always. 2-cycle. So if you notice, we have 2 here, 4, 3, and then 1. Okay, so we have a 2-cycle again. Okay. Now, as I mentioned, you can stack left on right or right on left. In the diagram, I'm sorry, I claimed that we were going to do the simplified version, and I keep bringing in these more advanced things. But On the diagram, it says R, LR. R, LR. Well, what's the R for? It means random. A random left-right. Well, it's random up to a point. So random LR means that, okay, well, let's see. We need to get back to an AMP. So let's do that. Oh, by the way, here's another way to get back to an AMP is just deal out the cards into half the number of cards you have, and then go ahead and stack them. Actually, you can stack these in any order because you've already paired them. Okay, great. So, okay, so here we're back to an AMP. And so what I wanted to show you was an RLR. And now what that means is, so as we deal out left, right, so I have left, right. Ordinarily, this next one would go left, right? Correct? But what you can do, as long as you build up the structure, you build up your levels, you build up both levels before you move on to the next one. Okay, so I don't know if you noticed what I did. Well, I'll do it here. So ordinarily this would go here left, but you could actually go over here. But we have 3 here and only 2 there, so we need to finish that level. And then you can come over here or there, it doesn't matter, and then stack those. And the amazing thing is, it's a 2 cycle. How is that possible? How is that possible? Well, it is. So it's now a 2 cycle. And it's starting to look a little messy. If you look at how the colors and the values are starting to kind of mix up. The other one I wanted to show you is, it's called an upjog. It's an automorphism on mirrored structures, and that's on the diagram. But it also converts AMP packets to 2 cycles. So an upjog is where you push the top card over, and then maybe you can do evens or odds. So here I'm doing an even position card gets moved forward. The next even position card, which is the 4th card, gets moved forward. The 6th card gets moved forward, and then the 8th. And then you strip these out and randomly stack them. Aren't we glad for that? So that will go from an AMP to a 2 cycle. So here we have aces, 3, 4, 2. That's a 2 cycle. Okay, and you can do an even upjog, which is what we just did, or an odd upjog. That's where you push the odd position cards forward. Okay, I think that's enough for one day. I'm pretty tired, so we'll see you in class. And if you can practice these and master these and get a sense for why they work and how they work, we can look at the proofs that confirm that they in fact do convert these structures, either preserve a structure, so where we're looking at an automorphism, or an isomorphism where they're converting structures from one kind to another. Okay, well, thanks for watching.